Class 11th Chemistry, Unit 7 Equilibrium, and in this video we are going to discuss about ionization constants of weak acids and weak bases. First of all, ionization constants of weak acids. Consider a weak acid HX that is partially ionized in the aqueous solution, and this ionization can be represented by this equation HX. When dissolved in the water, it will form H3O plus X minus. Initial if Hx is 1 and when no ionization is taking place, the H3O plus is 0 and X minus is also 0. If alpha is the degree of ionization, now what is the meaning of this degree of ionization? The strength or ionization ability of an electrolyte is expressed in terms of degree of ionization. It is defined as the ratio of number of molecules which dissociate into ions to the total number of molecules of the electrolyte. Okay, suppose if we are having the 10 molecules, total molecules of electrolytes are 10, and out of 10 if 3 are dissociated, so we can say 3 by 10, this is the degree of ionization. Okay, now this is represented by alpha. So at equilibrium, Hx remain 1 minus alpha and H3O plus become alpha and X minus will also become X alpha. If C is the concentration, that is molarity, so we can write equilibrium concentration of Hx is C 1 minus alpha, equilibrium concentration of H3O plus C alpha, equilibrium concentration of X minus is again C alpha. According to stoichiometry of this equation, when its one molecule is dissociated or ionized, we will get the 1 of H3O plus and 1 of X minus. So when its alpha molecules are ionized, so we will get alpha of H3O plus and alpha of X minus. Is that clear? Now for this we can write the equilibrium constant. Now in this case, actually this represents the ionization of weak acid, so we use Ka for acid, and this A is for acid and this Ka is called dissociation or ionization constant of acid, and this is concentration of H3O plus multiplied by concentration of X minus divided by concentration of Hx, and this H3O plus, that is hydronium ion, can also be written as concentration of hydrogen ion. So we can also write Ka is equal to concentration of hydrogen ion multiplied by concentration of X minus divided by concentration of Hx. So Ka is equal to, now concentration of hydrogen ion is C alpha multiplied by concentration of X minus, this is again C alpha, divided by concentration of Hx, this is C 1 minus alpha. So this C is cancelled by C, so we can write Ka is equal to C alpha square divided by 1 minus alpha, where Ka is called the dissociation or ionization constant of acid Hx. At a given temperature T, Ka is a measure of the strength of the acid Hx, that is, larger the value of Ka, the stronger is the acid. Now if we take the negative log of this Ka, we will get pKa. So pKa is equal to minus log Ka. According to this relationship, if Ka is higher, then pKa will be smaller. So for the stronger acid, pKa is smaller. Now according to this relationship, Ka is equal to C alpha square divided by 1 minus alpha. If we know Ka, initial concentration C of an acid, it is possible to calculate the equilibrium concentration of all species and also the degree of ionization of the acid and the pH of the solution. But if degree of ionization is very less, then in the denominator this alpha can be ignored in comparison to 1. So we can write Ka is equal to C alpha square, or we can write alpha is equal to square root of Ka by C. Now come to ionization constants of weak bases. This equation represents the ionization of this MOH into M plus and OH minus, and for this we can write expression for Kb. Now Kb is the base ionization constant or base dissociation constant, where this B represent for base. And this is again same. In the numerator, we will write the concentration of product. In the denominator, we will write the concentration of reactant. Now, again, if we assume that initially the concentration of MOH is 1, then when no dissociation or ionization is taking place, the concentration of M plus is 0 and OH minus is also 0. If alpha is the degree of ionization, then at equilibrium it remains 1 minus alpha. It is alpha and this is alpha. If C is the concentration, then we can write the equilibrium concentration of MOH is C 1 minus alpha. Equilibrium concentration of M plus is C alpha. Equilibrium concentration of OH minus ion is C alpha. Now, again, this equilibrium concentration, if we put in this formula, so we will get Kb is equal to C alpha multiplied by C alpha divided by C 1 minus alpha. This C is cancelled by this C. So, Kb is equal to C alpha square divided by 1 minus alpha. Now, again, if we ignore this alpha in comparison to 1 in denominator, so we can write Kb is equal to C alpha square, or we can write alpha is equal to the square root of Kb divided by C. Okay. Now again, if we take the negative log of this Kb, we will get Pkb. So we can write Pkb is equal to minus log Kb. Now again, this Kb represents the strength of base. If Kb is higher, it means base is stronger. So, but according to this relationship, if Kb is higher, Pkb will be smaller. For stronger base, Kb is higher and Pkb is smaller. Okay. Thank you. Subscribe my channel to get the next video from this chapter. And in the next video, we will discuss about the relation between Ka and Kb.